2c plus 4d. That hasn't changed. We still have the conservation momentum. But now I have 7 minus 3 is equal to d minus c. This is the new equation for the one-dimensional perfectly elastic collision. Solving for c is a lot easier now, or d, whichever one you want. So d from this one is equal to 4 plus c. I'm now going to take that, plug that into here. So I have 26 is equal to 2c plus 4 times 4 plus c. 26 is equal to 2c plus 16 plus 4c. 10 is equal to 6c. C is equal to 5/3 or 10/6 on your mood, meters per second. And d is going to be 4 plus that. So that's 1 2/3. This will be 5 2/3. We get to the same place. The advantage of this is we don't have to deal with a quadratic. The math is simpler. The disadvantage is we don't get that immediate feedback because we somehow eliminated the non-collision solution. Questions up to here before I ask a follow-up question about that? Back on the screen. What happened to the non-collision solution? I mean, when I did it before, we had the solution what we started with. What happened to it? Why did that one get eliminated and not the other one?
It's the one you cancel it out.
How so? Why did that eliminate the non-collision solution?
Which one is the non-collision solution?
One where we got 7 and 3. Oh. And Ryan speculated it's when we cancel it out. So why does that eliminate that solution? You're close.
Because it's no longer squared, so there's not a plus or minus version.
Well, that's why there's only one solution, but why was that solution removed and not the actual answer? I commented that the math people tell us as long as I divide both sides by the same thing, it's okay. There is an exception to that I did not mention. When can you not divide both sides by the same thing and have a legitimate solution?
You divide by 0.
Yes. So, in the non-collision solution, A is the velocity of the 2 kilogram mass before, C is afterwards. This works as long as A and C are not the same, or D and B are not the same. And they are only the same if that doesn't actually collide. So that's the point in which we got rid of, that's the point in which, when we divided by this, that's actually the point where we got rid of the other solution. Anyway, second method. Any questions? Third method. third method I personally find the simplest. The downside is it's conceptually more difficult. So what I want to do is I want to find the zero momentum frame. So we will start out with what I'm going to call the lab frame or the problem frame. This is, we're standing on the side, these are the velocities that we know. So P1 initial, actually before we do that, so for the 2 kilogram mass, V1 initial is 7 meters per second. Not satisfied with the way I'm displaying that. I'll just list it under here. So V initial, V1 initial, lab frame, meters per second. So that's 7. So P1 initial is 14, and this would be Newton seconds, kilogram meters per second, or whatever you're going to use. Over here for this one, V2 initial is 3, that's meters per second. And so P2 initial is 12. So P total, otherwise capital P initial, is 26. And that should be, this is just writing up what we've done in a slightly different form. We're going to be changing the velocities. So this is why I have the velocity set out, because the momentum's going to change if we change the velocities. We're keeping the mass the same. It's classical physics after all. All right, questions about this? All right, so now what I want to do is, so this is, how fast they're going depends on, we're just sitting on the sidelines, watching them go. Except now I want us, as observers, I want us to be going 7 meters per second in that direction. So if we're going 7 meters per second in that direction, the same direction as the 2 kilogram mass, how fast will this be going from our point of view? So it's going 7 meters per second that way relative to the classroom. I'm going 7 meters per second relative to the classroom. What is the velocity of the 2 kilogram mass? Yes. So observer velocity of observer, 7 meters per second. So that'll be going 0 meters per second. And so the initial momentum in this frame, that would be 0. So if I'm cruising along at 7 meters per second in that direction, what is its velocity?
-4.
-4. And so its momentum would be -16. And so what's my total momentum?
-60.
Yeah. The physics should still be the same. I should still have conservation of momentum, and I should still have conservation of kinetic energy in this problem. And not written on the board anymore, but just a reminder, it's a perfectly elastic collision. So now, let's change our observer. Our observer now is going to be going 3 meters per second. what becomes zero?
The right-hand side.
Because now I'm going the same velocity as it's going relative to the classroom, and so from my point of view, it's at rest. Well, what is the velocity of this now? If I'm moving at 3 meters per second that way, 4. And so its momentum is 8, and so what's the total momentum?
8.
Now what I want to try to do is I want to try to figure out how fast the observer needs to travel in order for the total momentum to be 0. Notice that when I go from here to here, I subtracted the velocity of the observer. Same here. When I went from here to here, I subtracted the velocity of the observer. So to find the 0 momentum frame, I need to subtract whatever the velocity of the observer is going to be. So I'm going to do 7 minus whatever the velocity of the observer is, times 2, plus 4 times 3 minus v equals 0. So I'm trying to figure out what do I need to subtract from each velocity in order to have a total of 0. So this is 14 minus 2v plus 12 minus 4v equals 0. I have 26 equals 6v. V equals 13/3. Let's just see if there's a mistake there. So now I'm saying we want the observer, the velocity of the observer, to be 13/3 meters per second. So 7 minus 13/3, see that's 21/3, 8/3. So this would be 16/3. Over here, I subtract 13/3 and I get negative 4/3 times 4, negative 16/3. And so now when I add those, I get 0. We have found the 0 momentum frame. So this is the 0 momentum frame. So in this point of view, as an observer, if I'm traveling 13/3 meters per second, what I see is these two objects coming towards each other, and they're going to collide. In this reference frame, what is their momentum after the collision?
0.
Yes. Because physics doesn't change just because the observer is changing. So we now have changed the problem into I have a 2 kilogram mass heading to the right at 8/3 meters per second, and I have a 4 kilogram mass heading to the left at 4/3. 4/3 meters per second. They're going to collide and bounce off each other. If the total momentum is 0, that means that after the collision, one of them has to have a positive momentum, one has to have a negative momentum. Or they'll stop, but if they stop, we lose all the kinetic energy. And so it's no longer perfectly elastic. So they will bounce off each other, and they have to go in opposite directions. So after the collision, what does the velocity need to be so that I have the same kinetic energy? Logan, you look like you have an idea.
Do we use 1/2 mv squared?
Indirectly. We don't need to calculate with it, actually. So, tell me about V and 1/2 mv squared. What does it mean? V. Yes. Not velocity, it's speed. So if the 2 kilogram mass has the same speed afterwards, and the 4 kilogram mass has the same speed afterwards, I know my kinetic energy is conserved. But I know that the velocities won't be the same. So how can I change the velocity so that my speed is still the same, but my velocity is not?
Where the speed stays the same,
Same.
but the velocity changes.
Yes.
For both or for original?
We'll just do this one for now.
The velocity is constant.
No, velocity changes. Speed is constant. Well, speed before and after are the same. Speed does change during the collision. I'll care about those before and after.
When it changes the direction.
So if afterwards, the 2 kilogram mass is going to the left at 8/3 meters per second, and the 4 kilogram mass is going to the right at 4/3 meters per second, my speeds are the same for each object. My momentum is still 0. The only difference is instead of having 16/3 plus -16/3, I'll have -16/3 plus 16/3. All we've done is flip the signs, the sum is still 0. So in the 0 momentum frame, the velocity of the 2 kilogram final is -8/3, but I need to get back to my original frame of reference. Well, to get out of the frame of reference, when I went from here to here, I subtracted 13/3. To get back to the original problem frame, I just do the reverse. I add 13/3. Which is 5/3. Over here, I have 4/3. And then again, I need to add 13/3 to get back to the original frame, and I have 17/3. And that's the answer that we got doing it the other 2 ways. I'm going to do one other thing and then sort of recap it. If this had been a perfectly inelastic collision,
Oops.
perfectly inelastic collision, what's going on?
Momentum is conserved.
Okay, and
Kinetic energy.
it's not. Perfectly inelastic.
Oh,
What happens in the perfectly inelastic collision? Oh, Natalie, you have to look like you knew the answer. Sorry. Perfectly inelastic collision. I think it was the first type of problem we started with. With momentum.
Inelastic mean is just doesn't give at all.
It depends on which textbook you're talking about. Inelastic, the way that perfectly inelastic. Yeah, it's on the textbook. Some textbooks say perfectly inelastic means that, or inelastic means that there's loss of kinetic energy. In some textbooks, it also adds that the objects stick together.
Oh, yeah.
So perfectly inelastic is what I used for they stick together. So before, I know I have 26 Newton seconds or kilogram meters per second of momentum, because we've solved that several times. Afterwards, if they've stuck together, the total mass is 6, and that's V final. And so we get 13/3 meters per second. That is the same velocity as the zero momentum frame. That's not just coincident. For a one-dimensional problem, that's always the case. So the way I would solve this problem, and this is just, I'm going to show you my notation, not necessarily the way that your notation would be if you want to adapt or adopt this method. What I'm going to do, figure out my total momentum beforehand. So 2 times 7 plus 4 times 3 is going to be equal to 6 V final. V final would be 26/6 or 13/3. So the first thing I do is I solve the perfectly inelastic collision. Now, I got my 2 kilogram and my 4 kilogram. Before, lab frame. This has going 7 and 3. Shift. So minus 13/3, minus 13/3.